Hi there. You missed class, so I wanted to catch you up on what we did in class this week. The first thing we did is looked at our periodic table and we colored it a certain way. In other words, we wanted to show the different families. This family right here in red, these are the alkali metals. This family in orange that you see, they are the alkaline. They're specifically the alkaline earth metals. This family in this kind of reddish here, this big box, the D block, they are the transition metals. Then we've got over here, this is the noble gases. Our halogens are the yellow group. And these here are kind of misfits, so they're not really going to be considered any real family. And then down here we can see you have the lanthanide and the actinides. The lanthanides and the actinides. So the lanthanides is this whole row here, and the actinides is this bright pink one on the bottom. So these are the different families, and they're families because they are similar to each other. Just like you and your family, everybody might have brown hair. Everybody in the family might have blue eyes, something like that. These families have similar things too. And our goal for this past day that you might have missed is to talk about what similarities does everybody in the families have. So the first thing you should do is probably label your periodic table so you have these parts too. We actually colored them. In other words, we outlined, like did a box around all the noble gases and each of the families. That way we had them all set up to go. And what we did is we used those to color in this chart. So you can see I've got group 1, group 2, 13, 14, 17, 18. And that was just me doing another way. You can see these groups up here. Group 1, or the alkali family. Group 2, the alkaline. We did 17, 18. And the second part of what we were looking at is, can we read graphs and determine what kind of similarities we have? So on this chart, I'm looking at radius, that's size of the atom, as it compares to atomic number. Atomic number tells us the number of protons. Atomic number is these big numbers here. 8 for oxygen, 7 for nitrogen, 6 for carbon. And so we wanted to look at this chart and be able to read the graph. So let me show you about the graph. This group 1 here is the green. And that's this line right here. So I can see this is all of the family 1. So here's lithium is number 3. 1, 2, 3. Lithium is right here. Sodium is number 11. Number 11 is right here. And then we kept going down and we saw 19, 37. Here's 19 and here's 37. And I saw that as I went down the periodic table, my atomic radius actually increased. So as I went down, it actually got bigger in size. That's what I could read from this chart. The other thing I was looking at is what happens when you go across the periodic table. Notice this is group 18 over here, and they are these ones down here. And group 18 happens to be my noble gases over on this side. So if I have my alkalis, which are right here, and that is my group 1. That means on the periodic table, it's this group right here on the far left. And as I move across the periodic table, I can see my lines here. Sorry, they're a little faint in my copy work. And I can see that as I go across the periodic table, it becomes lower. In other words, over here, the noble gases are the smallest. The noble gases are here on the bottom, and they are the smallest family. So, you know when you go, like a football player, he's a really big guy. Those football players are big. They'd be like the alkali family because they are the biggest on the periodic table. While the noble gases are the smaller family. They don't usually play football probably, right? Because the big people who are kind of larger might play football. So that'd be our noble gases. And what we did, we talked about that and we put that on our notes. So here's my note sheet for you. We looked at atomic radius. And we looked at it as we go from one side to the other. And as we go down. And we just saw by using the data, by being able to read the data, that it got smaller as we went here, the radius, or in other words, the size of the atom, and it got bigger as we go here. And we kind of talked about why would that be? What's the because of that? Well, if you look at the atomic radius, we'll go up and down because that's an easier one. This is the first group here, the first row. You would call this 1s2, right? So it has one ring or one orbital, 1s. Down here it's called 7s. That means it has 7 spheres to it. So here's my nucleus. 1, 2, 3, 4, 5, 6, 7. So why would it get bigger as you start at the top and work your way down? Why is francium so much bigger than hydrogen? It's because it has so many more energy levels. I'm writing bigger because you add energy levels to hold electrons. The electrons live on these rings, or these orbitals, and we have to hold so many electrons. There happens to be 87 with francium. We have to put lots of rings on there. And so if you add more rings, you can kind of see that the atom gets much bigger. It's different though up here. Like if we're going to look at something, let's just look at across row 2. So if you are in row 2, that means you have 2 rings. Here is my lithium picture right here. As I go across, it gets smaller, but it still only has 2 rings, like if I was to draw neon. It's just smaller. And so the reason would be why? Well, the first reason is because you have the same number of energy levels. But, because right there, if you have the same number of energy levels, you might be thinking, well, then it's the same size, but they're not. The data tells us they get smaller. The data told us it gets smaller, so we need a because behind that. So my claim is it gets smaller. The data or the evidence is right here, the chart. Oh, that's the first one. Right here, the chart tells me it gets smaller. And now I need my reasoning. Like, what's happening in the atom that tells me it's like that? It's smaller because you have the same number of energy levels, but more protons. So if you think about it, if you're an electron, you live out here, or you live out here. This electron right here is being pulled in by the protons. That's what's holding it in. This electron over here is held in by the protons too, but it's so much closer because it has so many more protons. This one here has 3 protons. This one over here has 10 protons. If you have a 10 powerful magnet here, you're going to be able to pull those electrons in closer than something that only has 3 magnets here. 3 magnets can only pull this hard, 10 magnets can pull in this hard. So it's going to be smaller because you have the same number of energy levels, but more protons to hold the electrons in closer. Sorry, I have to go a little fast because I only have 10 minutes to make this video, according to the program I'm using. Okay, so then we went to our second chart, first ionization energy, and we read this data too. Now notice for this one, my group 1, or my alkalis are this first family right here. My group 1 is down here on the bottom. And my group 18 is this pink faint line. My group 18, which is the noble gases, live up here. So the first thing I can see is, like with group 18, it goes down. As I move down the periodic table, it decreases in ionization energy. I can see also that if I started with the alkalis, that's over on the left side of the periodic table, that's down here, and I move to the noble gases are much higher. That means as I go across the periodic table, it gets bigger. So I'm going to add that to my notes here. We're talking about ionization energy. Ionization energy. Ionization energy is the amount of energy needed to remove an outer electron. And I saw by the data that as I go across, this gets bigger, and as I go down, it gets smaller. So let's start with the up and down. Why? Why would it be? So once again, my claim is ionization energy gets smaller as you go down. My evidence for that is this graph. This is the data. Data is your evidence. And then my reasoning is the because behind it. The what's happening inside the atom kind of because. So ionization energy gets smaller. That means the amount of energy needed to remove the outer electron is low. If it's low, that means it's easy to remove an electron. And the reason for that, or the because, is that if you take a look at this atom, look at this electron, and how far away it is from its proton. The proton is the thing that holds it in. That's its magnet. That's pretty far away. This electron here, it's only so close. That's really close. It's easy to hold on to him. This electron being really far out is hard to hold on to. So it's easy to remove an electron because the protons can't hold it so tight. Because it's so far away. If I go side to side up here, it's the same kind of trend. Ionization energy gets bigger over here. That means it's hard to remove. It's hard to remove an electron because look how close it is to the protons. It's easy to take, it's really hard to take it out because it's so close to protons. Over here, it's further away. It's a lot easier. So it's hard to remove an electron because the electron is close to the protons. Once again, I'm sorry for going fast and low on time. What I'm sending to you to do, and what the other class has, everyone has as homework, is looking at electronegativity. That chart you'll see in here, you're going to color it according to these families. So just like I colored it for you here. And then you're going to answer the questions that's on the back. Do the very best you can. We're going to start it with talking about that when we meet next time. And then you'll also find a lab. So there's two other trends we want to talk about. This one's electronegativity, and the last one is going to be metal reactivity. Now we did a lab in class. I can't really simulate that lab for you, but I have a video here that looks at it kind of equally. So you'll find this document in Classroom, and that will kind of replace the lab that we did in class, since I can't really give that to you at home. So that would be your bits for homework. 1, color this and answer the questions. You'll find the document in Classroom. 2, you'll find this lab document, and you'll be watching a video to get your data instead. And you'll be finishing that in Classroom. I'm actually going to give you feedback on that, so I'm going to grade it on a rubric. You'll see that there, to see how well you're doing by stating your claim, your evidence, and reasoning, which is our whole focus going on here. So there you go.